carbonates are developing, and so forth. So it's a wonderful spot to do that. I'd like to acknowledge my co-authors. You see them up here. Al is here. Naresh couldn't be here. Peter's off in India right now, and Sujata is also busy. They all have contributed to this work. This work's really going to be the summary of a number of talks I've given in the past, but the main purpose of this is actually to show some of these brand new discoveries that some of you are aware of, especially if you're interested in the pre-salt in Angola. So we're starting to get some significant discoveries like over on the Brazilian side. And I'm actually going to get us all the way up to the equatorial margin and take a look at some of the recent discoveries on the Brazil equatorial margin and compare them to the African equatorial margin. And at the end, I'm actually going to give you a new model I've been working on for the opening of the South Atlantic that explains some of the things that we see in the seismic data. Now, this span data is just incredible. You can see examples up here, and we'll stick around later afterwards. But it allows us to get ages for ocean floor by knowing when the age of the sediments have come out on them, so we can really do things in a regional sense that hasn't been able to be done before. Not to mention imaging all the way through the crust and actually getting a feeling for how these basins form and how we get these petroleum systems initiated with source rock development. So again, I'd like to thank Ion Geoventures. I'm going to be showing seismic data from Angola, Congo, and Gabon up here at the top, Equator span, Nigeria span, and then we'll get to the other side where we have these various spans in Brazil that go all the way around the continent now. And it's really quite impressive what they can do to provide these images. So I also like to acknowledge the imaging process. So with that start, let's look at these data sets. This is the data sets I've been working on really for about the last 8 years plus other ones. But everything that's shown here has actually been acquired, but shown in the more of this yellow color is currently being acquired, infills in these areas. So right now there's almost 100,000 kilometers that's out there on the two margins themselves. I've also colored in a couple of the large fracture zones that help us reconstruct this margin. Now, I'm going to now talk about a summary of these various petroleum systems for those of you that aren't familiar with the area. And I'm going to start with one of the first ones, which is up here in Nigeria. And this would be actually using source rocks that are above the breakup unconformity, so they're like Paleocene, and the reservoirs are all above this breakup unconformity as well. And these were discovered in the 50s onshore, and of course, then they moved further offshore. In time progression, we then go to Angola in about the 60s. They started to have a source rock that was in the pre-salt, and it was actually sourcing reservoirs that were in the post-salt, mainly carbonates. And so that started about the 1960s. Then we really hop over to Brazil's first discoveries, which would have been in the Campos Basin, and they were similar in the fact that they were based on a pre-salt source rock, but then they also had a post-salt reservoirs of carbonate and plastics there at that time. So that gets us up to about the 70s. You'll see not much happened in the 80s, but that's when we started bringing on our deep water technology. So now in the 1980s, 90s, we started to have these very deep water discoveries. This would be the Jurassic, which we're using, again, a post-breakup age source rock, plus there's a pre-salt source rock in these areas, and going into these tertiary sands. And that's, again, responsible for some billions of barrels of oil of the Jurassic type of place. And then, of course, in Brazil, what maybe got most of you here is, and really about the 2000s, we started to get the Tupi, Jupiter, and that whole play, and I'll show more details on that. But that was a pre-salt source rock, sourcing pre-salt reservoirs and using the salt as a seal, which is really the most simple petroleum system you could hope for, versus having to get through the salt into the post-salt. And then the most recent, again, recently up here is getting up to the transform margin and looking at some of the discoveries up here along the African equatorial margin. These, again, are using either the very latest of the Syn-Rift or earliest drift of the source rocks, Albion and so forth, from Sedimanian, and then Cretaceous sands, turbidites. Now, what I'm going to talk about today is really these more recent discoveries. So Petrobras has had a couple of discoveries that are proving these petroleum systems, similarly with post-breakup age source rocks going into post-breakup age reservoirs. And most recently, there's been an announcement of some pre-salt discoveries in Angola, which are like the Brazilian pre-salt discoveries. So we're using a pre-salt source rock in these sag basins along with a pre-salt reservoir. So these are just brand new. And so the main purpose of the talk is really to introduce that data to you, let you see what it looks like, and then also to give you some background into how these margins are developed. So you're going to hear terms I'm going to use about sag basins and Syn-Rift. And sag basins are basins that form when we actually thin the crust, but we don't go to where we generate oceanic crust. So the crust gets thin, we end up having a Syn-Rift section, and then the faulting stops and we develop these sag basins. So they're the areas that we get these very rich source rocks. This would be the Lagoa Thea and the Falcao organic deposits of Angola. When we have the successful rifts, we actually drift away, and we have a lot more volcanics in these successful rift margins. So lots of volcanics, and in the case of the salt basins, we actually get salt. Now we see these volcanics filling in the Syn-Rift section because we can see them thickening into the faults, thanks to this imaging of being able to see through the salt. And we actually see the style of salt tectonics changes dramatically, and it's actually going to be the style of salt tectonics associated with salt being deposited in active gravas. These are keys to identifying these units when we look on seismic data. Now, if we put them together, we can actually work out the relative timing, and we'll actually see as this sag basin comes up, it gets broken, and it's like a nice symmetrical steer's head, the old Mackenzie model with pure shear, breaks up, and we'll actually see that the sag basin is faulted. And it's faulted by the more recent Barremian rifting. So we had a failed episode of Valanginian rifting, and then we actually get the Barremian rifting that breaks back through. So that's the model I'll be showing. I'll be talking about these sag basins because we're talking about petroleum systems. We need some source rocks. And here's a typical seismic line. I'll put scales on all these because I hate talks where they don't have scales. But you can see this is about a 700 kilometer long line. This has been imaged to 25 kilometers, and nowadays we routinely take these down to 40 kilometers. You can see that fairly smooth breakup surface here overlying the sag basin. There's the Tupi discovery, here are the source rocks. You see the more complex style of salt tectonics where the Barremian rifting is broken back through, and we get pretty good image for the base of the crust. Okay. So we'll come back and look at that line as we go on. But these are some of the terms I'll be using, and this is the model I use for how these rifts develop. I don't have time to go into a lot of details. I'll show you where these are at. So, of course, you're not interpreting if you're not making maps. So someone gives you a talk and they don't have a map, I say, what does it look like on the next line? Well, what I'm showing you is we've been able to use all these lines through here, and we can see this same area where the sag basin developed in the Valanginian, shown here in green, on both sides of the margin. Here's the reconstruction point. There's some volcanics here and there, so we have to move this back up to the north to have the actual conjugate margins. And then in blue is the area where we actually have the Valanginian rifting. So the failed rifts give us more of the steer's hole geometry, where the sediment's thin, and they're thickest in the area where we thinned the crust but didn't go to oceanic crust. And then where we have a successful one, we have a more classic Mackenzie type model where we have half a steer's head on each margin. Okay, now we're going to take a look at two seismic lines. We're going to look at one here in Angola, right through the southern Congo Basin, and then we're going to look at in more detail at the same line we looked at a moment ago. Here are these two lines. I've updated these slides as there's more discoveries on the Brazilian side. So we start up here in Brazil, and again, note the scale. This line is twice the scale of the Angolan line because the margin is much longer, so I had to squeeze it up a bit. Here's the sag basin shown in green. Here's where the Tupi was drilled. Underneath all this, you see in yellow up there is salt. The salt's very thick. On the West African side, once again, the geometry looks very much like a steer's head. The edge of the steer's head is broken by this Barremian rifting coming back in, broken by Barremian rifting. So in the Brazil case, and this is one of the petroleum systems we'll be looking at, here's Tupi, which is probably 8 billion barrels. Here's Jupiter out where we have the same source rocks, but now they've actually been faulted and they're sitting in rotated blocks. And so that actually the source rocks out here are sitting in a pre-rift setting of the Barremian rift versus actually being in the sag setting of the Valanginian. So now I'm going to show one of the other things we can do with all this regional data is actually do paleogeographic mapping. And there's a section that we can see beneath the Valanginian sag, and it's actually an older section that I'm getting fairly confident is probably about Jurassic. It could be older. We're not sure the age. And so everywhere I've been able to see this section, I'm going to show you in a little bit later, future slide, I've shown where it's at. So I think there was actually an earlier Jurassic episode of rifting which failed, put down the sag basins, and we had a Valanginian series of rifting which failed, and then the Barremian was successful. in these areas that are on white or where we're missing that section, and we'll see that it's been uplifted, eroded off, and then subsided down to make this room for a sag basin in here prior to anyone's ideas of when these continents could start separating. So the continents are still connected. We're still not extending them by any great amounts, and yet we generate basins that have up to 8 kilometers of sediments. And the Brazilian side, the African side, we see some of this up by the old cratons in Gabon, where the crust is colder and more rigid. And this was just brought out in the re-imaging done on Congo Span 1. They've gone back to these data sets that are older now and using getting the velocities a little better through their imaging techniques. We can see things much more clearly. There's actually a little down here next to the old Angola craton as well. So now let's move up and say, what did this area look like in the Valanginian during the rifting? Well, I told you I live in a rift. So, I expect to see mountains and valleys, and, I wish we had lakes in our valleys. We just have some lavas, and it's pretty dry. But at this time, all the highlands are shown here in brown, and all the lowland lakes during the Syn-Rift time are shown in blue. So you can put yourself in one of these lakes and imagine looking up at these mountains. In this case, these mountains are actually made of a Precambrian crust. On the Brazilian side, we didn't have nearly as much going on. We're not going to make as much room for the sediments either. Now, there's where the Jubilee discoveries are. Notice they're on top of these old Valanginian horse blocks because their crust is thicker, they remain structurally high, and the hydrocarbons migrate up to there and get trapped into the salt. On the Angolan side, similar settings here, but there's a lot of highs that haven't been looked at yet. Now I'm going to show you this, and this is actually showing you how thick the Syn-Rift sediments are. Now we're going to look at the overlying sag basin, and the sag basin on the African side is much more fully developed than it is on the Brazilian side. You've seen from the seismic examples. In fact, we have up to 8 kilometers of just sag basin sediment sitting in here. The maximum we get over on the Brazilian side is about 4 kilometers of sediments. So once again, here are the areas that are sitting on these old high blocks with these rich source rocks in the sag basin off to the side, going into the oil window, generating hydrocarbons, and migrating up onto these highs. So that's this pre-salt petroleum system with pre-salt reservoirs. And we get a lot of carbonates developing again on these highs and on these interbasin lines. And then lastly, here's the actual successful rifting, showing the COB, showing here in red, half the steer's head. And you can map that around. Interesting enough, there's actually Bahrainian rifting that tried to break off and have this part of the Santos fields end up in Namibia, but it stayed on the other side. Likewise, we'll see examples up here in Brazil, up here in Gabon, where Brazil almost took the offshore gravity low over the other side. So breakups are messy. You don't know who's going to get what oil field or what part of the mountain. Keep that in mind. So now let's actually go and take a look at some of the pre-salt discoveries. We're going to start down here. Here's the Santos Basin with Campos. Many people aren't aware that they're getting some significant pre-salt oil discoveries in the Campos Basin as well, because the Sag Basin's up there, and it's in the oil window, and they had a very similar lake system that went all the way up. And right now, this is where the really big discoveries are. We're going to take a look at this line right through here at the Jubilee field again. We're actually going to look at it in 2 orientations. Here it is uninterpreted, so if you're falling asleep, now you have to start doing your own interpretations here. But you can see a fairly smooth base salt. This is top salt, it's a very thick salt. You see the Sag Basin, you see some big faults. That might help you a bit. So here is the Sag Basin, again, depth scale, so we've got 3 or 4 kilometers of sediments in this case. And we start to see some reflectors down here underneath the Sag Basin, and these are Jurassic. I'm going to give you another look at it in just a moment. Here would be the area of the Jupiter discovery. So again, very thick salt, source rocks in the oil window migrating up and being trapped underneath the salt. Here's a slightly different orientation of 375, and in this case, quite clearly we can see these Jurassic sections that existed. It's been uplifted and eroded off by the Bahrainian rifting here, and if we went further over there, we'd actually see it was truncated by the Valanginian earlier rifting as well. So if you're in a lake over here in the Sag Basin time, you would actually look up and see sediments in these rocks, where in Angola you can just see volcanics and granite. So we can rework sediments in Brazil, put those back into the basin. So let's go to the Angolan side. Here's again, I'll talk about the Kwanza Basin. It's down here in the south, Benguela further south. Here's the Congo Basin. We look at the discoveries in the pre-salt in Brazil, there have actually been a number of them. In fact, in 1957, they discovered an onshore field called Kwanza, which they drilled through the salt, had oil in the Kubo transgressive sand right beneath the salt. A very small field. The next really successful ones were they would drill more deeply here in Kwanza, get down to the pre-salt. They found again some carbonates, toka carbonates, and they had oil in them. Congo had similar plays where they went down, but very difficult to depth image back at that time, so it was hit or miss whether you find a structure. They're pretty much found by accident, and then they'd simply step out. Then in the 80s, we got the Rabikunga onshore Gabon field, and then down the south in the 90s, we started to drill these highs in the Kwanza Basin, and as you'll see, the discoveries I'll talk about later are in the same area. And just for reference, we're going to look at the seismic line. The Jurassic tertiary fields are sitting right in that area. That's why that line is bent. We couldn't go through it at the time we were acquiring it. And just where we're heading in this talk, I'm going to show you this seismic line for a regional look. Then we're going to come down and look at these two boxes where Cobalt's had their discoveries in Block 21, and then down here where Mars has had their discovery in Block 23. And then we're going to end by taking a look at this line 4000 up in Gabon and say, how much further can we take this pre-salt play? Is it only down here in the south? Well, there's areas where we're going to push those source rocks way out of the oil window with burial from the Congo fan. And we'll see there's a lot of potential left for this play. Okay, here it is uninterpreted. There's the, again, the Kubo surface up in here. That's actually the source rock unit, this bright zone right in there. Here's the Basin sag. Put an interpretation on it. What's interesting is this sag basin actually got down below sea level during the Valanginian and probably had a salt layer put in, because we can see up-dip extension and down-dip compression from both flanks, and these faults aren't linked to anything deeper. So this gives us some idea about the elevation and the paleogeography at that time. Then the area was uplifted by the Barremian rifting, the incipient Barremian faulting, and brought this back up into a lacustrine environment. So we put oil windows on here. We can calculate those. I'm not going to get into that in great detail, but it does show you that in this particular case, our sag basin sediments are just sort of at the limit of being in the present day oil window. Again, with the salt putting it here to cool it, we can actually push that oil window down a little bit further. That's some work that Craig's done for you. Okay, now let's go look at what you can get off the internet if you're interested in this. This is actually from Cobalt's website. Here are their two blocks, 20 and 21. I put a little article that Al got off the internet over there that was just released today talking about their discovery here, not bicarb, but this Khmer. And then down here is the Mars blocks. Let's look at the Cobalt. They actually have a structure map in here where they're showing the series of highs, which are just like the highs I showed in the paleogeographic mapping that we did 7 years ago with the span data, early span data. And here's the discovery that they're now actually, they had trouble with this well. They've moved back to here, and they're now going to start to try to see the extent of that field. It's, I think, 44 API oil, and it's flowing 5,000 barrels a day, so we're looking at some significant results now. So we're looking at two seismic lines, a dip line that goes between the two fields, and that's all we have, and then a strike line that gets fairly close. So here's that dip line. Again, now we're imaging down to 40 kilometers, and the pink color is actually the crust. We see these deep crustal reflectors. Who cares, you say? Well, it helps you decide what's happening, where these faults are, how the crust has been moving. We actually have a lot of volcanics. This is up in the Block 7 area. These would be Valanginian age volcanics, Syn-Rift volcanics from the failed Valanginian rifting. And then we had the sag development. We're going to zoom in here now. Oh, sorry, before we do that, this is one of these structural type displays we look at that helps identify deep structure and helps us, again, see some of this faulting that goes down deep. This is something that has been developed by the imaging group. I'm going to show another one of those in a moment. Okay, here's that line zoomed in up shallow again. Again, this is offline, but the basic play are these high horse blocks, volcanics coming out on top of it. Again, Valanginian age, sag basin development, source rocks that we can take right to the Falcao wells, not far away, and then carbonate developments on top of here, and that's what they've been drilling and been successful with. So it looks very much like what we saw in Brazil. So again, there's the carbonates, there's the source rocks, and we see lots of mounding down within this area. Right where you'd expect it, on the flanks and on these interbasinal high blocks. now we're going to look at the strike line, similar setting coming through here, and this is actually right on the well. That's the proper TD. Here would be that breakup unconformity, and here would be the source rocks, and again, this carbonate play, and to come back in here now to drill a second well, and that's where that press release was from. So that pre-salt play that we saw existing in Brazil, here it is, here it's working, here they're producing. If you looked at that poster over there, I worked with Senegal, and we gave this poster in Cape Town in 2010, and said, here's all the areas that we're going to have discoveries in pre-salt, and that's right where they're drilling. So these data sets can be used to predict where you should be going and how to use them. You know, and they all have these data to use. So let's look at the last discovery of Azul. This is down in Block 23. Once again, here's the Precambrian basement dropping down a horse. In this case, we don't have as much volcanics. This looks like more of a sedimentary Syn-Rift section. Could actually have lakes and source rocks during the Syn-Rift, and then the big sag basin on top. I've colored this in so you can see that this is a much more complicated salt structure in this area. We're getting more salt there, and it's going to be much more difficult to image. So let's zoom in. Okay. So here are the salt structures. That's where the Azul is just about on this line. We can see some bright packages underneath here. I guess I didn't bother trying to draw any carbonates in because again, our imaging is at the best with these more complicated salt features above, but that's the same general point. All right, now let's go up to Gabon and kind of wrap up the salt basins, and then we're going to move to the equatorial margin. You can all hold on to your seats. Falling off yet at the speed of this talk. All right, so here's Gabon. Here's a big map of the area. So here's that sag basin coming all the way up here. So we've seen that the play is now working down here at these recent discoveries. Same areas we had before, but this is Block 21, 20, different wells are described in that poster. Is it going to exist on top of every one of these highs? Well, I want to show you a line now from way up here sort of into this basin and see how similar it actually looks. This is Gabon. That's a big offshore gravity lobe. Here's one of these structurally enhanced imaging. We can see oceanic crust with the moho. We can see this very deep crust going down to 40 kilometers. Once again, huge old craton in this area. So we can actually see some. We're going to zoom in here now. So you can actually see this sort of Syn-Rift looking structures in here. And what's interesting about this area, here we go, let's actually put the interpretation on. Just a quick one. But we can see faults that are going all the way through the crust. There's actually relationships between these faults and what we see in the moho. You can see a Syn-Rift setting, sag basin setting, but this is actually the Valanginian sag. So this is probably the Jurassic faulting that was up here. And I'll show you in a moment how this relates to Brazil, but this is probably a Jurassic older sag basin that existed here. That became the pre-rift for the Valanginian rifting, which became the pre-rift for the Barremian rift. So here's the seismic data on that same scale. There's oceanic crust. Here's the moho going down. There's the lower crustal unit. We'd use this for estimating heat flow by putting more production in the upper crust. That's down here in the lower crust, putting in the moho, isotherms. And here would be the Jurassic sags. Here's that Syn-Rift, failed, put down the sag basin on top, and we get a little bit of expansion above that by the Valanginian rifting, put a Valanginian sag basin sitting on top of there. What's interesting, there's actually faulting of the Kugel, or the Chela, whatever you want to call it, down up here to the surface. So this is a spot where almost this piece of crust got taken over to the Brazilian side. And other than that, it's smooth as can be through here till we get to a very narrow zone of Barremian rifting. So we can put together this timing and map these things out. There's the crust. Here's the Jurassic sag basin sediment with the Syn-Rift beneath it, and then here would be the Valanginian sag basin. So there's where we had no Barremian rifting, smooth as can be with the velocity models we put in. Here would be an area where we see just a little bit of faulting, and there is the area where we've actually extended the crust and generated oceanic crust in a successful Barremian rift. Zoom in one time to see if we can see any carbonate plays here. Well, there's the base salt. Here's the sag basin, that's the source rock unit. And I think with a little imagination, you can start to see some actual kind of mounding and onlaps onto some of these features. So I think there is potential for the same play existing all the way up into Gabon. Okay, so quick review. What did we just do? We looked at the pre-salt discoveries over there that were matching up with the Santos. So now Brazil's play is showing up over on the Angolan side. I talked a bit about this Jurassic section up here, and the Jurassic has been drilled in wells in the offshore Recto Cabo area. So these basins, again, would just close up along these tracer fracture zones, and so it makes sense we'd have a Jurassic basin up in here as well. So what are we going to do now? We're actually going to look at these recent discoveries. Now, we have some literature we can show you. There's actually seismic examples out there. I don't have enough time to put them in. It's not the good seismic data I work with. So they're only time sections. I haven't even used the time section. I don't know how. All right, so then we're going to take a look up here where we really have source rocks that are either in the very latest Syn-Rift or in the earliest drift. So here are the plays, here are the big discoveries. This margin has been broken up by various authors into extensional segments and into strike slip segments. So these are strike slips shown in red, extensional in black going across here. Here are the discoveries, Jubilee, Venus, and then this is the new tunnel discovery some of you may have kept track of as well. And I'm going to show two recent discoveries that are proving the petroleum system based on Petroleum's drilling. And I'm also going to emphasize the importance of this Romance fracture zone. Even though the fracture zone itself isn't important, we're going to see the geology changes dramatically, and it tells us about how the continents actually separated and the timing of their separation. And that will lead into this new model of the opening of the South Atlantic. So, again, you can get this stuff off the internet. Here's Ghana, so here's where the discoveries are in Ghana. This is actually maybe Albion down here. That's Turonian. Turonian's good source rock around the world too. And then these would be the fans in there. Same thing up here in Sierra Leone. Maybe Albion or Cenomanian underneath here. They're not really sure. Turonian in there. And then these upper Cretaceous sands. So that's the play that's been working along the equatorial African margin. And again, here's this Romance fracture zone, and all this stuff is going to be north of that Romance fracture zone. And we're talking about a post-salt source rock, post-breakup source rock, and a post-breakup reservoirs. And Tullow, just again off the website, they're drilling a very similar thing over on the equatorial South American. Again, this could be Cenomanian or Turonian in here as source rocks, and they've drilled into these deep water flats. It's interesting enough, on the other side of this big high, that's actually a Jurassic age rift. So there's multiple phases of rifting along this margin as well. And the one they're in here now is actually. So here's some of the basins along the Brazilian equatorial margin. I mentioned the source rocks are either just beneath this unconformity or sitting above it. We actually do see a little Valanginian sag basin when we're south of the Romance, but not north of it. The main play, and then we also get Albion and Aptian carbonates above this breakup unconformity. North of the Romance, the Albion and Aptian is all on oceanic crust, as I'll show. So it's actually are opening up at a more recent time north of the Romance. Here are all these various clastic deep water sands, are the main reservoirs. And there's actually a carbonate, a Ligocene shelf edge we can see that comes through underneath the Amazon. So here's the one line in the south. I'm going to rush through this. Here's the position. Here's the nose sticking out of Brazil. We're looking at a discovery that's right off the shore of Sergipe. Here's where that well was drilled. When you first look at this line, I was scared by how much volcanics were here. I don't like petroleum systems with 2 or 3 kilometers of volcanics, meaning the salts that come up through the crust. But here's where they drilled their well, and there's our Albion Aptian Turonian section, and it's right in the oil window. So even though we had a fairly significant, volcanic episode here, we put these sediments down later, and it's a cooling episode. When we bring these magmas up, they're actually able to have a light oil discovery. So that's Espirito Santos. Again, on this side, we're going to hop way up here and look at one more example. So now here's the Amazon River coming out. Here's again, some of these oceanic transform faults or fracture zones coming through. And we're going to look at this line right there. Here's the other discovery in the Brazilian block. Again, image down to 40 kilometers, thick crust. We get really dramatic changes in crustal thickness across these transform margins, which again has quite important implications in terms of maturation modeling, and we'll show that in just a moment. Not that much volcanics. Here's that volcanic layer laid down. And then we get Albion sediments and then Turonian. Again, all sitting on continental crust. And we're going to find out we don't get any sediments on oceanic crust until the Turonian. So that's going to be significantly younger than what we get south of the Rome Ridge. Of course, we're going to zoom in. Oh, so in the case of this oil window, we've done some 1D models up here on the shelf by putting in the various thicknesses of upper and lower crust and get a top of oil window around 3,000 meters with good radiogenic heat contributions. As we thin the crust, we lose that. We're now 6,000 meters beneath the seafloor. And by the time we get out into oceanic crust, you need at least 8 kilometers of sediments before you're going to be able to push any potential source rocks into the oil. So let's zoom in and take a look at this play. So here would be the Albian, Turonian coming in here. This is an area where we get all this up-dip extension, down-dip thrusting. So we got a thrust belt that runs all along this margin. And the actual play is going to be right in this area. So again, this block is a little goofy because this is off of our line. The line just barely goes through here, so the well is significantly out of the plane. But it gives you a feeling for the type of environment that they're drilling into here, these sort of Cretaceous turbidites. And I heard they re-entered this well and drove it down and had more oil shows than they had when they had some trouble with the well shell. There's that oil window. So it's important to calculate these things and figure out which of your potential source rocks are capable of generating them. Just about done. Now we're going to get into the plate reconstruction work we've been doing lately and talking about the importance of this romance fracture zone. So let's put here's the last 2 spots we just looked at. These are the 2 discoveries by Petrobras. So it's starting to establish the petroleum system up on the Brazilian equatorial margin of South America as we continue on to Ghana. There's the Romance fracture zone coming through here. South of there, we see actual salt basins, smaller little bits of salt that are in here. We see some volcanics and actually SPRs. So these are thick volcanics that merge into the oceanic crust. When we go north of the Romance, we get no SPRs. We get thick volcanics that are all sitting on top of continental crust themselves. And we also see no salt up there. So now let's go up to the Albian and Appian time. Now we can actually see that the Albian is pinching out on oceanic crust. The red line is the continental oceanic boundary through here. So that means we have opened this up by Albian-Appian time. North of the Romance, all those sediments are being put into what looks like very deep pull-apart basins associated with this Romance, which would have been a continental strike slip fault at that time, and matches with the timing of the basins in Chad, Benue, and so forth. So, one more time to put this together. What was happening paleogeographically? Here's the late Appian, 115 million years ago. We get some salt all south of this Romance. Up here, we're just developing these very deep basins. There's up to 5 kilometers of Albian and Appian in these basins underneath the Amazon fan. So let's put Africa in here. It's all attached to this point. About 120 million years ago, south of this BP fracture zone in here, we started to generate oceanic crust, and we started to see some Appian sediments actually making it out past the COB and onto oceanic crust. Okay. And at that same time, though, all the sedimentation up here were in these intercratonic basins. I don't call them failed rifts because they don't really look too rift-like. They develop so rapidly, I think they're actually pull-apart basins along the strike slip faults. And it ties in again with the Central African shear basins that are in Chad and so forth, which are in about those locations. So at that point, when the Romance is working, all this is Africa, but that's still part of South America. So this is the shape of Africa. It's over here. We're allowing this part of the South Atlantic to open while we haven't opened north of the Romance yet. Okay, now if we go to the 105 million years ago, we've got the Albian coming out onto oceanic crust, Albian out onto oceanic crust. So we've generated oceanic crust south of the Romance. We've actually essentially glued these 2 parts of Africa together. So Africa is now moving out this direction, but that's still South America. So the Romance is active, but these things are moving out and allowing oceanic crust to generate. All of our sediments are still on the intercratonic basins. And the last one I'll show you now is the first sediments we see getting out on the oceanic crust, the Turonian. So by Turonian time, Africa had been assembled and was moving out. So what happens when you use any of our plate reconstruction tools and you use the present-day shape of Africa and it closes up? Who's been successful? There are no hands. You get overlaps, you get a lot of problems because Africa didn't look like Africa until 100 million years ago. So I'm going to take this one step further and show you we've done this work all the way from the south coming up and try to tie in with these different petroleum systems. So the other really major fracture zone, which is really a continental strike slip fault, is the one that comes down here and goes into the Paranal Basin and comes across the, I forgot the name of it, Florianopolis Ridge and so forth in here. So we tried to open these cratons were separating. We're making ocean crust south of the Rio Grande Rise, Walvis Ridge. We get lots of volcanics because it paused here and it couldn't break through. That failed rift resulted in the generation of the Valanginian Sag Basin in Brazil and this Valanginian Sag Basins in Africa. So these cratons are moving apart, or the heat's thinning the crust in these areas. Down here, the cratons are actually moving apart. Finally, it found a spot at about 125 million years and broken the Barremian in the sections I was showing you where the salt basins are. There's a little pause north of the Campos for about 5 million years. Here, the Angolan craton and the Gabon craton and the Sag Basin from Africa over there. Then hopped up here, again paused for about 5 million years. And the next really big pause is up here where it again took about 15 million years. So you can just envision this, that Africa is being assembled piece by piece until it finally gets its present day shape at about, again, Tronian or something, and it moves out. Again, a lot of this is just because we get wells, tops, take it out, and make them do that job. So, taking around the whole world, and I can almost let go of your seats now, but I really wanted to show you a lot of stuff today in terms of some of these petroleum systems, what's been producing, how these lines that go across the conjugate margins, we can take ideas from one margin and start to apply it to the other. And it can generate entirely new ideas, and even how the South Atlantic could be opening that explains what we see on the seismic data better than some of our current views. Thank you.
We'll take some questions now, and just repeat them to the people in front of us.
Yep, and also, I know a lot of people like to get out of here to get home and see their families. We'll be up here with the ion materials till we run out of beer. So we'll be glad to talk to you about things. So any questions? See, it was so fast no one can catch that. Go ahead.
What do you reckon the faces are forming those mounds that you've interpreted, pre-salt and Angola?
Yeah, I think they're carbonates again. There's a good talk in Milan about how they tie these in with the Valanginian cycles of arid and wet times, and when you grow your carbonates and wouldn't grow. And it was actually from field work in Argentina. But mentally, that's the model I have in here, is thinking about these carbonates growing during that time period. And where you see the mounding is generally on the highs. Now, again, just mere fact we can see in the pre-salt with PSDM data is good. And we really have to keep looking at the velocity models, and you probably want to do a research project to really get the velocities really accurate before you're drilling, 3D and so forth. But you really do see a lot of these moundings, and they're usually sitting on top of these basin highs. And I think the ones that are out in the middle of the basins, like Valea, which is a big basin high in the middle of this big sag basin, was an area that stayed high all the way up to probably the Cenomanian. So even after the breakup, there's actually no carbonates in the pre-salt around Valea, but it's all in the post-salt section. So that area stayed high and probably had ring carbonates around it, not on the top. And then the carbonates continued to grow up to probably the Cenomanian. Yep.
Do you see any evidence of differences in the salt velocities indicating that there could be some very interesting geochemical differences in the salt?
I don't think we can't do anything that accurately, but Al actually looked at a lot of logs. God spent more time working on volcanics than anyone in the oil industry should. But they're interesting. But lots of times these basalts are intercalated with sediments, and so their overall velocity isn't particularly different than the surrounding sediments. But we just see these the way I map volcanics are discontinuous bright reflectors. And once we can start seeing continuous ones underneath it, then I'd start going back into a sedimentary section beneath it. Along the edge of the Barremian Rift, though, we don't see much sediments left. Usually we go right from this sort of thickening wedge of volcanics into the normal faults, and then salt in there, but underneath it looks pretty much like it's basin.
One more question, Andrew? I have a question about when you gave that talk there. It was in conjunction with Senegal.
Yes.
What was the response from it? Did you get a lot of companies scratching their heads and kind of walking up to you guys?
Yeah.
What was the response there? Because obviously you proved it. Right?
And I let the Senegal people do the presentation. It was really nice. They were very proud of being there and giving it. They did. It really contributed a lot, brought in well information for us and stuff. And again, I started many years ago with Conical when we were doing the shallow water blocks, and the whole play was into the pre-salt, and then people just never trusted it. And so that's why I showed that slide of the historical development of pre-salt discoveries along the African margin. They've been there, but then to go out in the deep water and spend that money wasn't going to be there until they had so many examples from the. And who's been drilling them? It's been the small companies. It's been Cobalt and Mars that have drilled these wells even now out there to test these ideas.
Excellent. Okay, well, thank you very much again. Let's sit down.